minus trace of sigma by 3, which is known as sigma m, which is essentially sigma xx plus sigma yy. Okay, so sigma m is 1/3 sigma xx plus sigma yy plus sigma zz. Okay, now this is eventually gives us Sxx equals twice sigma xx minus sigma yy minus sigma zz, the whole thing divided by 3. Okay, and you can get the similar representation for Syy and Sz, and you can substitute those expressions in this expression right here, and that would eventually tell you that this whole thing turns out to be plus, as usual, here this 1/6 ends here, plus twice sigma xy squared plus. Okay, so you need to cancel this half, so eventually you get sigma xy squared sigma yz squared plus sigma zx squared. Okay. Now, in principal coordinates, this should eventually be written. From the first expression, it can be written as s1 squared s2 squared plus s3 squared. And we showed that the trace of s squared is an invariant, okay, which basically means, because this thing is an invariant and this thing is an invariant, so which basically means whether I write it in the global Cartesian or the principal coordinates, it's the same value. And that eventually would lead us to this expression. Another fun thing about deviatoric stress, if I take the trace of that and take a square of that, obviously it's 0, but that also means that s1 squared plus s2 squared plus s3 squared equals minus twice s1 s2 plus s2 s3 plus s3 s1. Now this quantity over here is as you can see in the principal coordinate, this is what the deviatoric stress looks like. Okay, so this right here is the I2 of S, and from that actually I can directly get this equals minus half of s1 squared plus s2 squared plus s3 squared. But now two things, one is trace of s squared, or rather this quantity right here, or this quantity right here, seems to be positive. Okay, because sum of the square terms and all are real numbers, so this essentially is a positive quantity. Therefore I2 of S is definitely not a positive quantity, it's a negative quantity. So instead we take something called J2. Okay, so J2 is minus I2 of S. Okay, you see it's not J2 of S, it's just J2, which represents the negative of the second invariant of S. Okay, okay. Now I know for a fact that most of you have not tried anything about it, or most of you do not understand as even today what are the things that I'm talking about. But that's not going to be healthy if you are continuing this course, and that's why I'm taking a lot of time in this topic. Okay, to make yourselves comfortable with the subject. And my suggestion is, find sources in the over the internet, look at your textbook, and look at the previous classes that we had, and make yourselves comfortable with this topic. Okay, there is a lot of matrix operation that is going on, linear algebra is going on. It's not very difficult, but if you don't practice, even the simplest thing would be difficult. Now uh, now from this we can proceed for failure theories. Okay, and I'm surprised when I ask whether you have tried something at home. Okay, at first you none of you answer, then some of you answer, and that is not also very convincing. Okay, uh, which is not a good sign, considering that I know for a fact, for over the years, this part would be uh, where most of you would find difficulty. So my suggestion is, if you are really serious about pursuing your ME, and if you are really serious about continuing with this subject, okay, so be also sincere about the topic that we are discussing. Achha. So the next topic is failure theories. I would discuss mainly three failure theories. So the first one is maximum principal stress theory. Okay. It says a material would fail, okay, if its maximum principal stress, I mean, there would be three principal stresses: sigma 1, sigma 2, and sigma 3. Okay, its maximum principal stress, the maximum of the three values, when that reaches a certain value, okay, when that reaches a certain value, then the failure occurs. I mean, you can call it the ultimate stress. Okay, when the maximum of the three reaches the ultimate stress, the failure occurs. Why did I mention ultimate stress? Was because this theory is more suited. It is found to be true. Of course, it's a model. Okay, material may show a very different behavior than a model. Okay, typically in brittle materials, this type of behavior is seen. Okay, so if I were to plot them in 2D, let's say there is sigma 1 and sigma 2. Okay, now this plane right here is one of the principal planes, the plane that is normal to n3. Okay, the third principal direction. And by plotting everything in sigma 1 sigma 2, this also means that sigma 3 is 0. Okay, that's why we don't need that coordinate. Okay, so that's just an assumption. And in your undergrads, most of the problems that you solve are plane stress problems. Okay, where with the third component of the stress would be 0 anyway. So be it your pressure vessel, or be it your combined bending and torsion, everywhere the stresses were in only the principal stresses were on a you know or the stresses were only in two planes. only in a single plane. Sorry. So it was a planar stress situation. Now let's look at so imagine this is the failure stress value, and I'm just generally calling it sigma y. Okay, but it can also represent the ultimate stress for brittle materials and yield stress for the ductile materials. So let's say this is sigma y. Okay, and this is the same length over here. Now at this point, sigma 1 sigma 2 are same. But if I move towards the left of it, sigma 1 is greater than sigma 2. Sorry. If I move towards the left of it, then sigma 2 is greater than sigma 1. So on this line, you have sigma 2 greater than sigma 1. And on this line, you have sigma 1 greater than sigma 2. Okay. So here you will be comparing the value of the sigma 1. And if the value of the sigma 1 is sigma y, then the failure occurs. Same goes over here. If the value of sigma 2 is sigma y, then the failure occurs. So this is what the failure surface looks like in the first quadrant. But you see, this maximum principal stress theory is in relation to the absolute value of the principal stress. It's not the sign value, but the absolute value, which means if one of the quantities between sigma 1 and sigma 2 turns negative, or let's say both of them turn negative. Okay. Now again, if I move towards this side also, okay, sigma 2 is still greater than sigma 1. Okay. And over here also, sigma 1 is still greater than sigma 2. So the failure surface continues. Okay. And and let's say both the quantities are negative. Okay. Then if you were to compare the sign values, okay, then sigma 3 would be the highest stress, which is 0. But it's not the sign quantities, it's the absolute quantities that matter. So basically, this turns out to be a square of dimension twice sigma 1. Now one can modify this. So this quadrant you can call it biaxial tension, and this quadrant is biaxial compression. And you know that in compression, material has higher failure stress than in tension. So what you can do is you can multiply with a factor when you are moving towards the compressive side, and you can make the surface look something like this. So the compressive side has the higher volume or higher area. Okay. Now what is the meaning of this failure surface is, if your stress state, okay, if your sigma 1 sigma 2 coordinate, if your stress state is, let's say, P, which is sigma 1 sigma 2, okay, given by 2, if your planar stress state is given by this coordinate sigma 1 sigma 2, okay, again, why are we doing this in principal coordinate system? Because then we'll have to deal with only two components of stress. Okay. So if your stress test is with P, and that P lies within the failure surface, then your structure or your component is safe. But if it goes beyond that failure surface, then the failure might occur. Okay. So, or if it is on the this so-called failure surface or yield surface, then the failure starts developing. So so that's what is the maximum principal stress theory. Now, second is maximum shear stress theory. Okay, also known as Tresca theory. Okay, so it says when the maximum shear stress, which basically means you take the absolute values of sigma 1 minus sigma 2 divided by 2, absolute value of sigma 2 minus sigma 3 divided by 2, and absolute value of sigma 3 minus sigma 1 divided by 2, and take the maximum of that. Okay, so take the maximum of those. When that equates to tau y is when the failure is occurring. When this expression equates to tau y, then the failure is occurring. Okay, so basically, look at the first quadrant. In the first quadrant, uh, acha, so this is tau y. Okay, now one more thing. Let's say in a tensile test or uniaxial tension, this is going to be on mode circle. Sigma over here and 0 over here. Okay, so if I were to write down the principal stresses, sigma 1 is sigma 2 equals sigma 3 equals 0. Okay, so maximum shear stress is sigma by 2, and the failure occurs when sigma equals sigma y, which basically means tau max is sigma y by 2. Now, if we assume that this material follows maximum shear stress theory, more or less, or Tresca criteria, then the failure only occurs when tau max is tau y. Now, which type of materials would follow such a material model? Since it is related to shear stress, you already know what type of material. More of ductile materials. Okay, so ductile materials, approximately be represented with maximum shear stress theory, and that shows the failure occurs when sigma is sigma y, and then the tau max is tau y, which gives us a relationship between sigma y and tau y, which is 0.5 sigma y, which basically means sigma 1 minus sigma 2 equals or so basically if I assume okay, so this basically gives us this relation: maximum of the three, that is this time signed quantities, not unsigned, minus minimum of the three is actually sigma y. Now, if you're on the first quadrant, the minimum is sigma 3, because both sigma 1 and sigma 2 are positive. So the minimum is sigma 3. Okay, so let's look at uh, this part of the curve. So this part is going to be the same. So as long as sigma 2 is less than sigma 1, we would only take sigma 1 and sigma 3 into consideration, and sigma 1 minus sigma 3. So equation of this line is sigma 1 minus sigma 3 equals sigma y. And same thing applies to this line over here. Here, sigma 2 minus sigma 3 equals sigma y. And since sigma 2 is greater than sigma 1, we only take sigma 2 into consideration of this representation. So the first quadrant is similar to the similar to the maximum principal stress theory. Even the third quadrant is same. How so? It's because, let's say you are on this line where sigma 1 is less than sigma 2 for sure, and sigma 1 minus sigma 3 equals, sigma 3 is 0 and sigma 1 is minus sigma y, which basically means sigma 3 minus sigma y equals sigma 1 is sigma y. So we would take this line and also you take this line. Okay. Now when it comes to the second quadrant, let's say, so in that sigma 1 is negative and sigma 2 is positive and sigma 3 is 0. Since sigma 3 is 0, it's no longer the lowest principal stress value. Sigma 1 is the lowest principal stress value, and sigma 2 over here is the highest principal stress value. And then the relation is sigma 2 minus sigma 1 equals sigma y. And this is the curve that you get, or this is the line that you get. Same applies to over here. And that's your maximum shear stress theory. Okay. Now, next comes distortion energy theory. Okay. So, distortion energy theory, before going to distortion energy, we should be in a position to define what is distortion energy. Okay. So, the distortion energy has this thing to do with epsilon v by 3. So the volumetric part of the string, and then there is the deviatoric part of the string. Okay, that strain, so the distortion energy, let's call it U, is defined as half of sigma inner product epsilon d. Okay, now you might recall what this means. It means taking summation over I, summation over j, sigma ij epsilon d ij. So taking term by term and taking a product and then adding them up. Now again, in this, the stress can be divided into two components. One is the hydrostatic part. Please note, this one is the volumetric part, and the counterpart in the stress is the hydrostatic part, and then there is the deviatoric stress. And I'm taking the inner product with this. Now for the first part, if I take inner product of an identity matrix with any deviatoric component, let's say S or epsilon d, whatever, that actually is the trace of S. Okay, and actually this can be shown that for any two arbitrary matrices need not be symmetric. Inner product AB is trace of A transpose B, trace of A B transpose, trace of B transpose A, trace of B A transpose. Okay, and also this is B inner product A by definition. Okay, so from that, or you can simply think of that most of the components of I are 0, only the diagonal components are 1. So when multiplied with the corresponding components of epsilon and then adding them up, I'm supposed to get trace of, so this is epsilon d, I'm supposed to get the trace of S or trace of epsilon d. So anytime you take the hydrostatic part or the volumetric part and the deviatoric part and do an inner product, okay, you are going to get a 0. We explained that with the principal coordinate system, that they are literally orthogonal. This is in a metric space, but even in the principal coordinates we can represent, let's say, with a hydrostatic axis that makes hmm, equal angles with the uh, principal directions. And then there is a deviatoric plane which is essentially normal to the hydrostatic axis. And because of that, there if I take any line on that, okay, any deviatoric stress and any hydrostatic part, the inner product is always going to be zero, or the dot product over here is always going to be zero. So that they are literally orthogonal to one another. And so basically what I'm trying to say here is this is only S inner product epsilon d. Okay, so if I proceed further, and go with the Lame representation of the stress, where stress is represented as lambda times lambda times trace of epsilon times I plus twice mu epsilon. And then what we did was we showed that it is lambda plus twice mu by 3 times trace of epsilon times I, where this is the volumetric strain, this is the bulk modulus, this is regular shear modulus, and then the deviatoric strain. So then we said that this is minus p times I and s. Okay, and again, this representation is unique, and we can segregate the deviatoric and the hydrostatic part. So k times epsilon v is minus p, and s right here is twice mu epsilon d, which basically means that this distortion energy right here is mu times S inner product. Okay, 1 by twice mu, or actually 4 mu S inner product S. Okay. Now, if you really think about it, this is 1 by twice mu, 1 by 2 S inner product S. Okay. Now, this S inner product S is, as you know, is trace of S squared. Okay. You take the S squared. Okay. That is a different matrix, and then you take the trace of it. Okay. And we just showed that this half times this quantity is our J2. Okay. So U is 1 by twice mu J2. Okay. So the distortion energy theory is that when this distortion energy reaches some critical value, okay, when this distortion energy reaches some critical value, okay, then the failure occurs. Okay, so now look at the failure. Look at the failure in shear. Okay, so J2, we saw there are various representations. For example, this is one of the representations. Okay, now consider torsion of a shaft or pure shear. Okay, so this is the Morse circle. So this is your tau. Okay, and sigma 1 is plus tau, and sigma 2 is minus tau. Okay, so if I substitute in this expression, so it is going to be 1 by 6 times 4 tau squared plus tau squared plus tau squared, which is tau squared. Okay, and the failure occurs when this tau is tau y, which means U critical is 1 by twice mu tau y squared. Okay, and this is the target value. This target value for the distortion energy when the failure must occur. Okay, now let's try this with the uniaxial tension. In uniaxial tension, again, sigma 1 is sigma 2 and sigma 3 are 0, which basically means J2 is 1 by 6 times twice, is it twice? Sigma 1 minus sigma 2 minus sigma 3. Should it be twice? Yeah, twice sigma y squared. Okay, or 1/3 sigma y squared. Okay, therefore the value of U critical for failure is 1/3 sigma y squared. Okay, so we would compare these two values of the critical distortion energy, because the distortion energy theory predicts that in each case the failure occurs because the distortion energy reached the critical value. So both are the expressions for the critical distortion energy, which basically means sigma y squared is or tau y squared is 1/3 sigma y squared, or tau y is 1 by √3 sigma y. Okay, so very familiar expression. Okay, now if I look at the expression for J2 right there, substituting for sigma 3 equals 0, J2 becomes this quantity. So the limit on J2 is J2 should be, so to be safe, J2 should be less than equal to tau y squared. That's the criteria. Now the expression for J2 becomes with sigma 3 equals 0, it becomes 1 by 6. Okay, I should delete something. So the general plane stress expression where J1 and sigma 1 and sigma 2 are general. So J2 is 1 by 6 sigma 1 squared, because sigma 3 is 0, sigma 2 squared plus sigma 1 minus sigma 2 whole squared. Okay. If I expand this, so it is 1/3 sigma 1 squared plus sigma 2 squared minus sigma 1 sigma 2, and that becomes an ellipse. Okay, with, to be frank, that actually is that is not an ellipse about sigma 1 and sigma 2 axis, but that is an ellipse about these two axes. Okay, and if you substitute one of the quantities such as sigma 2 equals 0, okay, in this, so J2 becomes 1/3 of sigma 1 squared, and then the limit on that should be tau y squared, or 1/3 sigma y squared, and then the sigma 1 should be plus minus sigma y. So basically on the sigma 1 axis the limits are plus sigma y and minus sigma y, just like the maximum principal stress theory and the Tresca theory. So all of these points, and if you take even sigma 1 equals sigma 2, okay, even then you see the sigma 1 sigma 2 is again sigma 1 squared. So again the values of both quantities must be plus or minus sigma y. Okay, so all of these points are part of distortion energy theory. All those coordinates. So this is what the distortion energy theory would look like. Okay, so this ellipse right here. And and if you are to trust, let's say Shabosh, okay, who is a scientist, who is a renowned scientist in plasticity, metal plasticity. So his claim is that most plastic and viscoplastic materials will conform more to the distortion energy theory than the maximum shear stress theory, and that is a blessing for us. Chances were, because of the fact that the Tresca theory is more conservative. That means if you are safe according to Tresca theory, you are definitely safe according to distortion energy theory. So, the fact that metals, conform to the distortion energy theory is a blessing for us, because it is a smooth surface, always differentiable everywhere. Unlike distortion energy theory, which is not differentiable on any of the corners. Okay, and because of that, I mean, why do we need to differentiate the surface? We'll learn that in the coming classes, but we need to do that very often. Okay, so with that we know that how the distortion energy theory can be used as a smooth surface, okay, for metal plasticity. Okay. Okay, so is it clear up to this part?
Yes, sir.
ওই পার্টটা আরেকবার বলবেন, J2 is equal to 1/6 into 2 sigma y whole square.
For uniaxial tension,
Yes.
look at the expression for J2. Okay, so there is I mean, the one in the left, okay, the total expression 1/6 sigma 1 minus sigma 2 squared, sigma 2 minus sigma 3 squared. Okay, so in that expression, sigma 1 appears twice, one in sigma 1 minus sigma 2 whole squared and sigma 3 minus sigma 1 whole squared. If sigma 2 and sigma 3 both are 0, then the second term is obviously 0, but the first and the third term.
Okay.
সবাই clear বলছো, and I'm not quite confident in you guys. Okay, so my suggestion is, don't just look at it, practice. Okay, try derive on your own. There is at least some portion where you are confused, you are stuck. It has to be. Okay, so whatever we did in the last class and before that, everything you need to practice. You should be able to derive all of that in one go, okay, without any assistance. Okay, for example, when I take your class, any of your class, I don't carry a note with myself. Okay, because it's so it's a continuous learning for me, and it's a continuous so if you can talk to any of your seniors, okay, they can tell you that whether I take a finite element course or theory of plasticity course, I just do it in a in an elaborative manner, in an extempore mode, so I don't carry a note. So it's because everything falls under logical sequence for me. There is nothing to derive, actually. I mean, nothing that we cannot derive from the scratch. Okay, so okay, so it is this figure you have seen in your textbooks, okay, in undergrads, in any of the design book that you have used, okay. I'm sure about that, but I'm also sure about that you have not been made familiar with the 3D version of it, and I'm also sure that you never paid so much attention into deriving or justifying each of these diagrams. So we have done that part, justification, but we also need to look at each of the failure curves in the 3 dimension. So it's no wonder if sigma 3 is non-zero, and this is what sigma 1, sigma 2, and sigma 3 look like. I'm also just drawing the negative side of it. Okay. It's no wonder that, one second. The maximum principal stress theory is given by this box. Okay. Just like it was given by a square in a 2-dimensional plot. Okay, the maximum principal stress theory in 3D is a box where each of the planes are either plus sigma y or minus sigma y. So it makes an intercept with one of the principal directions in plus sigma y and minus sigma y, and it's a plane parallel to the plane of 2 other principal directions. Okay, just like that. It's very simple. Okay. Now we are talking about maximum principal stress theory, like it is the most accurate representation of the brittle failure. Okay. The way we learn about brittle materials in undergrads, that for that, okay, it is fine. Okay, but you see, although it's a fact that you cannot have a working window in the tensile zone of brittle material uh, beyond certain stress value, in compressive part that stress limit is much higher, and even with that scaling of scaling modification that we mentioned in the just a minute ago, for the compressive side, that is not sufficient. Okay, and actually a brittle material would be more conforming to the so-called Drucker-Prager model. Okay, so there is your first assignment, Drucker-Prager model. One second. So if you find no other source, you can look into this paper. Okay, so that talks about Drucker-Prager model, and actually the more advanced and more generalized versions of the Drucker-Prager model as well, and its application. So you can go through this text and the reference of it to know about Drucker-Prager model. Okay, so you can actually take a screenshot or maybe write down the title of the paper. Okay, so that is your first assignment. So write couple of pages on Drucker-Prager model, giving all the mathematical representations and also the graphical representations, and explaining those representations on the way. Okay. So a Drucker-Prager model would be more accurate representation, more accurate depiction of how the failure in brittle materials occur. Achha. So the next thing is, if I were to plot uh, so the distortion energy theory. Now, it would have been great if we could represent all the failure surfaces, okay, on the same diagram, but I don't think that would be possible. So the failure criteria in distortion energy theory is J2 equals tau y squared, which basically means, or one third sigma y squared, which basically means, as we have seen, this is half of s1 squared plus s2 squared plus s3 squared. Okay, so basically s1 squared plus s2 squared plus s3 squared, okay, is is square root of 2/3 times sigma y whole square. Okay, so as we have explained earlier, sigma 1, sigma 2, and sigma 3. So imagine this is the plane, deviatoric plane, the octahedral plane that has the same intercept with the three axis. Okay, same intercept value. Now just look at the center of it. Okay, and this is the axis that goes through the centroid of the triangle. Okay, and this is the hydrostatic axis. So the this axis can be represented like this: 1 by root 3, 1 by root 3, 1 by root 3. Okay, so any stress state, any stress state sigma this stress state in the principal coordinates is a sum of the hydrostatic part. So this is the hydrostatic part, which is basically minus p times I equals sigma m times I, where sigma m is trace of sigma by 3, the hydrostatic part essentially. And then there is your derivative vector, not sigma 2 sigma 3 plane or sigma 1 sigma. So it components. So or any parallel set of planes. So what is your hydrostatic axis?